So we've talked about how enzymes function, and that's to decrease the activation energy. And we've talked about rate constants, which is a way of quantifying how fast a reaction goes or is capable of going, depending on the concentration of the reactants or in an elementary step, right? So what is the relationship between the activation energy and the rate constant? And so these are related to each other by the equations shown on the left, and we're going to go through these step by step. And what we'll find out is that the rate constant is not only dependent on the activation energy, but also on different influences as well. So here's the equation for what we're looking at. We're going to start with the Irene equation. So this is K, which is the rate constant for a particular step in a reaction. Okay, and that's related by this equation where A is a pre-exponential term that we'll talk about next. This is e to the negative EA over RT. Okay, so where EA is the activation energy, which we can also denote as delta G double dagger. It's the same thing. Okay, and in this term, EA is divided by R, which is the gas constant, and T, the temperature. Okay, so we call this the exponential term, e to the negative EA over RT. So here we see the influence of the activation energy on the rate constant. Okay, so the numerator contains activation energy, and so the higher the numerator gets, because there's a negative sign here, right? The higher this numerator gets, the lower the exponential term is going to become. So let's say we have an infinite activation energy. So just a kinetic barrier that's infinitely high. All right. So intuitively we say, well, that reaction is going to be really difficult to occur because, as we know, the higher the activation energy, the slower the reaction will occur. So mathematically, does that make sense? Let's take a look. So if this is infinite, so e to the negative infinity is 0. Okay, so the more that goes to negative infinity, the more the exponential terms become 0. A times 0 is 0, and therefore K, the rate constant, will become 0. Okay, so the higher the activation energy, the lower the rate constant, and the slower the reaction is. All right. Conversely, if there is no barrier, right, we would say, okay, well, that should be a faster reaction, right? So if EA is 0, right, that's going to turn this entire term to 0. We're going to have e to the 0th, which is 1, and the rate constant is going to be equal to just the pre-exponential term, which is the maximum that the rate constant can be. And so that's going to, so that mathematically is consistent with what we think of when we think of a barrierless reaction, okay, something with no activation energy. But there's another important term in the exponential term. So R is a constant, so that's not going to change dependent on reaction conditions, but temperature might, okay? And so the question is then, so how would temperature affect the rate constant? So take a second, consider if temperature would increase, decrease, or have no effect on the rate constant. So pause your video, and then we'll discuss.